Math 287, Cuesta College. I'm Joe Vasta. Let's go ahead and do review 4. We'll be working out some problems. This is 1.12, the review of your book. Number 18. I'm doing the evens because you don't have the answers to those. Well, you shouldn't, or I don't know how it works. And the answers to the odds are back there in case you wanted to do the odds. So here's another differential equation. X, y prime minus 2y equals 2x squared ln x. And already we see, this is not written in the problem. Now I'm going to start doing the problem. We see that x has to be greater than 0 because of that ln x. So I think on the test it will say this is a linear differential equation. Use the method of the integrating factor. By the way, this one is not separable, and it's not Euler-homogeneous, and it's not exact. And if you want it, you could verify those things. This is linear. The method of the integrating factor, before we start circling things and calling them p and f, we need a 1 in front of that y prime. So I'm going to divide everything in this equation by x. So I have y prime minus 2 over x, and I'll write it like that, times y, equals, dividing this by x, this gives me 2x ln x. Okay, I'm going to compute the integrating factor. I think I'll do that over here. The integrating factor is going to be e raised to some power. Okay, I think it's time to identify some things. This guy right here is p, and this guy right here is f, and p and f are continuous in this interval. I mean, from 0 to infinity, not including 0. So I'm not going to write that down. So the integrating factor is gotten by going e raised to the power of the integral of p. Okay, so the integral of -2 times 1 over x is going to be e raised to the -2 ln absolute value x. With the integrating factor, we can take our c to be 0, and we saw that in lecture. I'm going to go ahead and take the absolute value off that x. We don't need it anymore because x is greater than 0. And I'm going to take that -2 and, using the power rule of logs, make it jump up there. So this is going to be e ln x to the -2. This guy right here, property of logs, that goes pop. And so my integrating factor is x to the -2, or if you want, 1 over x squared. So why is that important? Because I would then use the integrating factor, multiply the equation by the integrating factor. So when I do that, I end up getting y prime over x squared, and this is -2 over x cubed y, and then the last one's going to be x squared on the bottom, x on the top, so this is going to be like 2 ln x all over x. Okay, and the whole magic, and it's really not magic, but the magic of the integrating factor is the fact that the left-hand side will always become d dx of y times the integrating factor. That will always happen. And the integrating factor in another problem might be the sine of x. It would be y times the sine of x. And you could always verify it. Watch this. This is the product rule. The derivative of the first, y prime, times the second. Okay, so that gives you that. Plus the first, which is y, times the derivative of 1 over x squared. The derivative of 1 over x squared is -2 over x cubed. So this does work. So that equals 2 ln x all over x. Okay, the next thing I'm going to do is I'm going to integrate both sides with respect to x. Put a little dx right there. and I have the antiderivative gun and the derivative gun. They're lined up next to each other, so what you end up just getting is y times the integrating factor. That will always happen. This equals, taking the integral of this, and before you start doing integration by parts, some of you might panic and do that because you see the ln, but what is the derivative of the ln of x? The derivative of the ln of x is 1 over x. And you have that right there. You have 1 on the top, x on the bottom. That's going to disappear. I'm doing the eyeball u substitution method. You could say u equals ln x. In any case, you're going to get 2 ln x squared over 2. And that x is going to disappear. And don't forget your plus c. Okay, so the 2's are going to cancel. And you're trying to solve for y. So y is actually going to equal x squared times that. So this is ln x. And make sure you put parentheses around that. That's not the same as ln x squared. It's ln x, and then there's 2 copies of that. So those are different. And then we have plus c. And there's an example that illustrates the method of the integrating factor. Okay, let's go ahead and do number 20. So, number 20 in 1.12 looks like this. It looks like y squared plus 3xy. And it actually says minus x squared. I'm going to put a plus x squared because I think that could be a typo in the book. I don't want you to start doing this on the test, like changing things around, but I'm going to go with this problem better because I think the other one leads us down a pretty dark path. I'm not saying it's undoable, but I'm going to go ahead and put a plus there instead of the minus. And this is a differential equation. We can probably verify that this is not exact. I mean, if this was p and you went py, you'd get 2y plus 3x. And then this is qx would be 2x. So those aren't the same. This is not exact. I'm going to go ahead and solve for dy dx. Okay, I want to get dy dx all by itself. So the first thing I'm going to do is that right there, and bring the negative x squared dy to the right hand side of the equation. So I'll just write x squared dy, divide both sides by dx, divide both sides by x squared, and I end up, I'll rearrange things too, dy dx equals y squared plus 3xy plus x squared. This is all over x squared. Now, looking at this, you can see that this right-hand side is not going to be separable. So this is not a separable differential equation. You could also see that it's not linear. Because if you try to write it so it's a linear equation, you have a y squared there. And so linear, all the y's and the derivatives of y have to be to the first power. So what this one's going to be is this one's going to be Euler-homogeneous, which you use the method of the change of variables. You do a v substitution, and that's what we're going to do. Now, on the test, they might give you something like f of xy equals something that looks like that, and ask if that is homogeneous of degree 0. The way you could do that, so let me go ahead and look at this guy right here. This is f of xy is y squared plus 3xy plus x squared. This is all over x squared. To check to see if this is homogeneous of degree 0, I mean, that's what will give us an Euler homogeneous differential equation. I don't know. Remember, let's see. I do remember. Okay. Plug that into the equation there, and I end up getting t squared y squared plus tx tyt. I'm hitting the tripod now, and then this is plus x squared, which is t squared x squared. Almost running off the paper there. This is all over x squared, which is t squared x squared. You can actually factor a t squared out of the top. So I have t squared, and this gives me y squared plus 3xy plus x squared. This is all over t squared x squared. The t squareds cancel, and you see that you get the exact function here, f of xy. So yes, f is homogeneous of degree 0. So that is for a two-variable function, which means that we can do this problem by change of variables. It's an Euler-homogeneous differential equation, and the change of variables we want to do is we want to let, this is like a u substitution, v equals y over x. Okay? And so that means that y is going to equal x times v. And we're going to plug that into here, and I will do that part in purple. Now, I'll remember that this guy right here, dy dx, is really d dx of y. That's what this guy is right here. So let's go ahead and make our substitution and see what happens here. We have d dx of y, which is xv. This equals y squared, which is x squared v squared plus 3x. So everywhere there's a y, I'm replacing it with an xv. And then the x squareds I'm leaving alone. Okay, so right here is the product rule. The derivative of the first times the second plus the first times the derivative of the second with respect to x is that right there. Meanwhile, on the right-hand side, we can factor in x squared out of the top. It kind of reminds you of what happened over there. We have v squared plus 3v plus 1. This is all over x squareds, and my x squareds are out of there. Now what happens on the left-hand side, that's always going to happen on the left-hand side when you solve Euler-homogeneous differential equations and you let v equal y over x. So what I have is I have a v there, and then I have this expression which is not a fraction anymore, so I'm going to subtract v on both sides. So I have x times dv dx equals v squared plus 3v plus 1 minus v. So I'm going to combine that with the 3v, the minus v, and this is going to be v squared plus 2v plus 1. Okay, so what we've done is we've just tricked this differential equation, which was not separable, into being a separable differential equation. So the next thing I'm going to do is I am going to separate this. We'll use another piece of paper. I'm going to separate this. So it says dv over that. So this is dv over v squared plus 2v plus 1. This is going to equal, it's going to be dx over x. Okay, so it's separable, and my variables are x and y, x and v instead of x and y. I'm going to integrate both sides. Okay, now to take the integral of the left-hand side, I might realize the bottom can be factored into v plus 1 times v plus 1. So I'll write it like that. And I can do a u substitution and let u equal v plus 1. I'm going to eyeball this one, so this is really this thing to the negative 2, and the derivative of that is just 1. So when, when all is said and done on this, I'm going to end up getting v plus 1. See, it's to the negative 2, so it's going to be to the negative 1. That's going to be over negative 1. This equals ln x plus c. Now we can say ln x plus c because we don't need the absolute value, because this x cannot equal 0, so we can just say that I'm solving this from 0 to infinity. If you want to keep the absolute value in there, you can, but I'm not even going to put it. Okay, so what do we have here? I'm going to multiply this equation by negative 1. So I have v plus 1 to the negative 1 equals ln x with a negative in front of it minus c, which is really what? What is minus c? It's just another constant, c. So this guy right here becomes 1 over v plus 1 equals, we'll just write it like this, c minus ln x. I'm going to go ahead and flip both sides, so I have v plus 1 equals 1 over c minus ln x. And I'll subtract 1. v equals 1 over c minus ln x, minus 1. I think I could actually finish this up here. That v, is actually y over x. So v is y over x. I'm going to replace the v with a y over x. So just write down the right-hand side of the equation. I'm going to multiply both sides of that equation by x. So this is one where I would probably say solve for y in the instructions on the test. So this is y equals x over c minus ln x. And then this is minus x. Actually, I should have changed back to black ink, but oh well, there is my answer. And so that is how I would do a problem like that. Euler-homogeneous, so I would, on the test, I'm going to tell you which ones they are, and then I want to see you solve that differential equation using that method. Let's go ahead and do another problem. Let's see, I've covered separable, linear, Euler-homogeneous. This is all of first order. And so the one that I did not cover yet was exact. So I'm thinking perhaps I should do an exact. That way we covered them all. So number 24 in section 1.12 will be an exact differential equation. And it looks like this. dy over dx equals sine y plus y cosine x plus 1. This is all over 1 minus x cosine y minus sine x. Now, if we're just taking a look at this, we can see that this thing is not separable. We can also see that this is not an Euler-homogeneous differential equation. If you put in ty for y and tx for x, there's still going to be a t. So not separable, not Euler-homogeneous. It's definitely not going to be linear because you're taking the sine of a y, and so that's going to make it nonlinear. This thing is probably exact. What I'm going to do is I'm going to go ahead and cross multiply. So I have 1 minus x cosine y minus sine x. This is multiplied by dy. This equals sine y plus y cosine x plus 1. This is times dx. Okay, I'm going to go ahead and put everything on the right-hand side of the equation. So a lot of writing here. and then I'm going to subtract that. So I'm going to write it out a little differently. I'm going to write it as the x cosine y is now positive, and so is the sine of x, and then minus 1 dy. Okay, so we're trying to see, I mean, maybe in your homework or on the test, they'll say, is this equation exact? A way to verify if a differential equation is exact is we identify that as P and identify this as Q. Okay, so really, if it was an exact differential equation, you'd have F, where you take the x derivative and you get P, and you take the y derivative and get Q. To verify that it's exact, you take the y derivative and take the x derivative there, and you should get the same thing. So if they're saying, is this an exact differential equation, you've had some of those in your homework, you would take the derivative of this with respect to y. Now, if I'm telling you it's exact, you don't have to do this, but I'll just do this really quickly. So the derivative of sine y is going to be cosine y. Okay, the derivative with respect to y, this is y times a constant. X is a constant when you're doing this, so this is going to be, it's going to be plus the cosine of x. Okay, so qx, so we're going to see if we get the same thing. If we get the same thing, then we're in business and we can solve this. Taking the derivative with respect to x, well, it's just x times a constant, so I'm just going to get cosine y. And then taking the derivative with respect to x of sine is the cosine, so cosine x, and then the constant 0. So it looks like py does equal qx. And so I'm going to put this in a little cloud here, because if we had told you the differential equation is exact, you don't really have to do this. Okay, so let's go ahead and see if we can write out our answer. To get our answer, we're going to go ahead and take the antiderivative of this with respect to x, and we'll take the antiderivative of this with respect to y. If there's some common terms that have x's and y's, we should see them in both things. So I'm going to go ahead and take the antiderivative of this. The antiderivative of sine with respect to x. So this is just a constant then. So it's going to be, like the antiderivative of 7 with respect to x is 7x. So this is going to be sine y times x, or I'll put the x first. So x sine y. Okay. So that one came from this right here. I'll just put arrows there. Now I'm taking the antiderivative, or the integral of this constant, and then times cosine x with respect to x. So I'm taking the integral of that. And the integral of the cosine of x is the sine of x, and y is a constant. So this is going to give me plus y sine x. And so that gives me that right there. And the antiderivative of 1 with respect to x, I'm going up this way, is going to be x. Okay, now let's go ahead and take the antiderivative of this with respect to y. Well, the antiderivative of cosine y is really the sine y. Here's a constant in front of it, so it will be x sine y, which has both x's and y's in there. So that gives me that one there. The antiderivative of this with respect to y, well, there's no y's in there, so this is like a constant. It's going to be constant times y, or y times this constant, which is that one right there. The important thing to do is not to write it twice. And then the antiderivative of negative 1 with respect to y is going to be negative y. So in calculus 3, that's the potential function. I'll go ahead and draw that there. When we do exact equations, you always find the potential function and set it equal to a constant. And that solves your differential equation. Okay, so that was exact. Now let's go ahead and look at the chapter review. think we'll do problem number 57. New piece of paper here. So make sure you know how to do those kinds of differential equations. 57 on 1.12 is a mixing problem. It says a solution containing 3 grams per liter of a salt solution pours into a tank. So what we have is we have a tank, and they're telling you a solution. They're telling you the concentration of that solution. So the concentration going in is 3 grams per liter of salt, and it pours into the tank. The tank is initially half full of water. So initially, half full of water. So when they say water, what they mean is pure water is in that tank. Okay. And they say the rate going in is 6 liters per minute. So Rn is 6 liters per minute. Okay, turn the page, and it says the well-stirred mixture flows out, so it's going to be flowing out at a rate of 4 liters per minute. So that's a rate coming out is 4 liters per minute. The tank holds 60 liters, so the tank capacity is 60 liters. Find the amount of salt in the tank when the solution overflows. So find amount of salt in tank at overflow. And the tank is definitely going to overflow because the rate going in is 6 and the rate coming out is slower, which is 4. It says initially half full of water, so actually that tells us the volume at time 0 is not 60, it says it's half full, so it will be 30 liters. The amount of salt at the beginning in the tank, well, it said the tank was half full of water. So when they say of water, that means there happens to be 0 grams of salt at the beginning, but right when it starts, like after 1 second, this is going to go up. So let's see how we do the problem. The differential equation that we always use is A prime equals Cn Rn minus R out A over V. So that is where we kind of always start, and we have A prime is Cn, which is 3, we see that up there, times Rn, which is 6, minus R out, which is 4, and then we have A over V. Now the problem is we always have this extra V, and we're like, well, what do we do with this? Well, with that extra V, we have to find an equation with V in it, V equals. We do start off with this right here. We do always know that we can go dV dt is the rate of change of the volume of the stuff in the tank. And so the rate of change is, well, 6 is going in and 4 is going out. The rate of change is going to be 2. Okay, it's going to get 2 liters per minute fuller. So this here is a differential equation. I'll zap both sides with the antiderivative gun. V equals 2t, this is with respect to t, plus a constant. And then I'm going to go ahead and put that one in right there to find out what c is. So I have 30 equals 0 plus c, c equals 30. So V has the equation. This describes the volume in the tank. It's 2t plus 30. Now before we plug it back into this differential equation, we do have to find on the amount of tank at overflow. Well, we want to know when the overflow happens. To find out when the overflow happens, the overflow will be right when the volume hits 60. So I'm going to put 60 in there, and this is going to help me find the time of overflow. So this is going to give me 30 equals 2t. 15 equals t. So at 15 minutes, that's when it overflows. That's when it starts to overflow. Okay, we'll come back to that. We're going to need that because really what we want to find the amount of salt in the tank at overflow. We're going to be going A of 15 to find our final answer. But to go A of 15, we need to know what A is, and to find out what A is, we need to solve the differential equation. To solve this differential equation, we have to put this V right there. So A prime equals 18 minus 4A over V, which is 2t plus 30. So this is A prime equals 18 minus 2a. I'm reducing this fraction, pulling a 2 out and canceling, and then I'll have a t plus 15. Okay, another piece of paper for this one. Okay, so I'm trying to solve this differential equation here. It's not separable because of this 18. I think it's going to be linear. We have A prime plus 2 over t plus 15 A. This is going to equal 18. So now I have to solve this differential equation. It's linear. This guy right here is P. This right here is F. And we see that P and F are continuous from negative 15 to infinity, but really we can say that we're going to solve this differential equation from 0 to infinity because we are starting the clock at 0. Okay, so the integrating factor, that's what we call I there. It's going to be e raised to the integral of p, 2 over t plus 15 dt. So this is e. We take the antiderivative of that. You can do a u substitution if you want. You're going to end up getting 2 times the ln, absolute value, t plus 15. We can take the c to be 0. We really don't need the absolute values because our time is from 0 to infinity. The 2 jumps up. We also don't need the absolute values because the 2 jumps up and it's squared. This thing here goes pop. And your integrating factor happens to be t plus 15 squared. There's the integrating factor. I'm going to multiply this differential equation by the integrating factor. So when I do that, I end up getting t plus 15 squared times a prime plus, okay, this is going to be multiplied by this, so it's going to say 2 t plus 15, this is times a, and then we're going to have 18 t plus 15 squared. So what do we say about this part in the integrating factor, the method of the integrating factor? This will always become d, in this case it's dt of y times the integrating factor, and y is actually going to be a in this example, a times the integrating factor. Once again, if you have trust issues, then you can go ahead and do the product rule here, the derivative of the first times the second, plus the first times the derivative of the second, which is actually that. And then this is 18 t plus 15 squared. Okay, what am I going to do on both sides? I'm going to integrate with respect to t on both sides. The left-hand side, we have the antiderivative gun next to the derivative gun. Those are going to neutralize, and we have a times t plus 15 squared. This equals, I've got to integrate this. I would do a u substitution. I'm going to eyeball this. So this is the derivative of t plus 15 is 1, so this is going to be 18. This something to the third power over 3, and then we have plus c. 3 in the 18 becomes 6 and a 1. And I'm going to divide both sides by t plus 15 squared, and I'm going to get the amount. The amount equals, it's going to be 6. So when we're dividing, be careful with these exponents here. This is t plus 15. And then I'm going to get plus c over t plus 15 squared. I wish I were done finding the amount function, but I'm not done because I need to find out what c is. To find out what c is, I have to use the initial condition that we wrote at the beginning, a of 0 equals 0. So moving on to another piece of paper here. A is 0 and t is 0, so that's what I'm doing to find out what c is. So this is going to be 6 times 15, which is 90, plus c over, that looks like it's going to be 15 squared. So 15 squared is 225. And so this is negative 90 equals c over 225. C equals negative 90 times 225. That's going to be negative 20,250. So let's go ahead and rewrite the differential equation. This one right here. The amount equals 6 t plus 15 plus, oh, I should have put minus, oh well, minus 20,250 all over t plus 15 squared. Whew. So our original problem said find the amount in the amount of salt in the tank at overflow. Overflow we found out was 15 minutes. So we have to put 15 into this. Okay, so if you do that in your calculator, actually this one you don't have to round. I did it in my calculator and I ended up getting 157.5, and then salt is measured in grams. Okay, so the follow-up question is, what is the concentration? At overflow. At overflow. I'm just making this up because I wanted to make sure we covered concentration. The concentration is going to be the amount, A of 15, over the volume, V of 15. And actually we know volume of 15, that's the tank capacity, so this is 60. And this is 157.5. Let me get, I don't know if I can't see the calculation on there, so I'm going to go ahead and use my calculator. 157.5 divided by 60. Is that what I... So we have 15. I want to make sure that 15 times 2 is that. 157.5 divided by 60. So I'm getting 2.625, and this would be grams per liter. And of course it's coming in at a concentration of 6, so it's marching its way up to 6. So if the tank had unlimited volume, you would eventually get to 6 after a long time. Okay, so that concludes this problem here with the tank. So let's move on to Chapter 8. So in Chapter 8, we learned how to solve higher order differential equations. And in 8.1, I'll just make up this problem. We have this linear transformation, L, which equals xd squared minus x squared d plus x cubed. And then they give you some function like y equals x e to the x. And then they ask you to find L of y. Okay, so that's the problem we're going to do. So how would I do this? Well, Ly equals this guy right here, which has derivative operators, and that one is not a 3. I just went ahead and accidentally put that there. That one happens to be a 2. So I write down this derivative, these derivative operators which are in this linear transformation, and that's going to operate on this function right here. So let's go ahead and write this out. We get xd squared, and then this is x e to the x minus x squared d x e to the x. And then the last one is x cubed, and then we have x e to the x. Okay, now here's a common mistake people do. They say, oh, well, we can write this as like x squared e to the x and x to the third, but really, because this x is on the left side of the derivative operator, we are not taking the derivative of that. We're taking the derivative of this. In fact, we're taking on this one 2 derivatives of this. So what I'm going to do up here, and maybe I should have done this first, is find out what the derivative and the second derivative of this function is. So the derivative is gotten by the product rule. We'd say the derivative of the first, which is 1 times the second, so this is e to the x, plus the first, which is x, times the derivative of the second. The second derivative is the derivative of e to the x, and then the derivative of this, which we just did, it's going to be e to the x plus x e to the x. So the second derivative can be simplified to 2 e to the x plus x e to the x. So there's the second derivative, the first derivative, there's y. We're going to plug them in there. So we have x times the second derivative, which is right there. Then we have minus x squared times the first derivative, it's just a d times that, which is e to the x plus x e to the x. And then this, we don't have any derivative, the 0th derivative, which is, we're just going to multiply those, so x to the 4th e to the x. So what do we have? We have 2x e to the x plus x squared e to the x minus x squared e to the x minus x cubed e to the x plus x to the 4th e to the x. What happens here? Well, on this one, these guys cancel, and you can write your answer like that. Because I'm lazy, I'm going to factor out, you don't have to factor this out, an e to the x and maybe an x e to the x. And then I have 2 minus x squared and then plus x cubed. So it all comes back to linear algebra. You have a vector here, and you sent it through this linear transformation, and now you have this vector right here. Let's go ahead and do another kind of problem that you would see from 8.1. This kind of covers 8.1 and 8.2. Let's see if we can do this. So I'll just say this covers 8.1 and 8.2. And they would say find the kernel of a linear transformation L. So this is a different L than the last problem. I'll write the L up right here. L equals d squared plus 25. Okay, so there's the problem right there. Find the kernel of that linear transformation. The kernel of the linear transformation are all the functions y. When you go ly, it takes you to 0. So I'm going to replace the L with a d squared plus 25. And then we have a y there. This equals 0. So this is d squared y plus 25y equals 0. What's the second derivative of y? It would be y double prime. And so what we got is we have a second order differential equation, constant coefficient, homogeneous, which we now know how to solve. We would write the auxiliary equation, r squared plus 25 equals 0, which kind of reminds you of the d squared plus 25. You'd find the solution, so r equals plus or minus 5i. And you would write out the solution to the differential equation here. Y equals c1 cosine 5. Now we were never given what our variable that we're taking the derivative of. I'll just use x's. Plus c2 sine 5x. Okay, so this is actually a linear algebra problem. It's asking you to find the kernel of this linear transformation. Here is a linear combination of two vectors, two seeds we were calling them earlier. So the kernel of this linear transformation is going to be the span of those two vectors, cosine 5x sine 5x. And so whenever you solve a homogeneous differential equation, you're really finding the kernel of a linear transformation. You are working with linear algebra, whether you like linear algebra or you don't. So that gives me the results there. Let's go ahead and do a little 8.3. So in 8.3, we have this function here, e to the negative 2x. We have 1 minus x cubed, and then we have sine 4x, and then let's go plus. Wasn't going to do this, but I think I should. E to the 5x. Okay, so they'll ask you to find the annihilator. Now, the important formula to remember for annihilators is when you have a sine or a cosine multiplied by an e to an ax, the formula is always going to be d squared minus 2ad plus a squared plus b squared. So that's the formula to remember. Well, actually, since this is a take-home test, you probably just have it, you just look it up or something. But and that could be some of the reasons why averages on the test have gone up, because these are tests you take at home, and people can look things up in their book or on their notes. So I knew the averages were going to go up, but since we're in a pandemic, we just do the best we can in terms of trying to make this an incredible course here. Okay, so we have this right here. In this right here, we know that A is negative 2, and then I'm going to ignore that because I will do that at the end, and I'll show you how I'll do that polynomial, and then B is 4. So when I do this right here, so let me just do this in red. This is going to be d squared minus 2ad, so that's actually plus 4d plus a squared plus b squared. So this is d squared plus 4d plus 20. Okay, so that really annihilates just if I had that right there. So what I'm going to do is I'm going to write down my answer. It's going to be d squared plus 4d plus 20. Okay, so that annihilates the red part, and then it's multiplied by a polynomial of degree 3. So in terms of annihilators, you can go back and look at the rules. There's going to be a 4 there. Now we also have to do the annihilator for this, which is just going to be d minus 5. And if you're trying to find the annihilator of the sum of some things, some functions, then it's actually the product of the annihilators. So I'm going to actually go this annihilator times d minus 5. And there it is. That's how you find the annihilator of a function. So practice some of those. Make sure you can do those. And now we are going to turn our attention on a differential equation, which we're going to solve by the method of annihilators. And then we'll solve that differential equation by variation of parameters. After that, I think I'll jump and do a Laplace transform. And then if we have time, we'll do something from springs and circuits and things like that. So this is 8.3, 8.7. We have a differential equation that says y double prime minus y prime minus 6y equals 10 e to the 3t. Y of 0 equals 0. Y prime of 0 equals 7. So it's an initial value problem. I'm going to solve this first. So I'll put Roman numeral number 1 by using annihilators. The method of undetermined coefficients is another name for that. And so when I'm doing that, I go ahead and I write out the operator equation with the d's. So this is d squared minus d minus 6 operates on y. And you can see that that gives me that differential equation. This equals, leave a space, 10 e to the 3t. Okay, so because this is the method of annihilators, we want to annihilate 10 e to the 3t. And I kind of put t's there instead of x's. That's all right. We'll just remember to put t's for our answers. I'm going to annihilate this by going d minus 3. And I apply it to both sides of the equation. And so when we do this, we end up getting d minus 3. This one does factor. I think it factors into d minus 3, d plus 2. That operates on y. This gives me on the right-hand side 0. We just tricked this non-homogeneous differential equation constant coefficient into being a homogeneous one. Now I can write out the auxiliary polynomial, but I'm going to find that I can see what I'm going to get. I'm going to get a 3 there, 3 there, and a negative 2 right there. So when I write my answer, which that's what I'm going to write now, I'm going to say y equals, and I'll start with this one first. So this will be c1 e to the negative 2t plus, okay, so check, I did that one. This one here, c2 e to the 3t. Okay, check, I did that one there. And the last part is going to be plus, and I can't put a c3, I'm going to put an undetermined coefficient, and I'm going to use like capital A, B, C. Your book, I think, uses capital A naught, capital A1, whatever. They've got some issues. I'm going to go A. And then, because I'm repeating this, I'm going to put that extra t in there. T, e to the 3t. Okay, check. So the rest of doing the annihilators is finding out what that undetermined coefficient is. And in fact, this guy right here is y sub c, the complementary part of the solution, which you would actually have to find if you were going to do variation of parameters. You would find that first. So we'll kind of talk about that, you know, when we do variation of parameters. And then this right here is your trial solution, or or the particular solution we call y sub p. I'm going to plug y sub p into the original differential equation. In order to do that, I need to take the first two derivatives. Do you see that? So I have y sub p prime is a product rule, the derivative of the first times the second plus the first times the derivative of the second. Okay, I need y double prime, which is going to be the derivative of this guy, which is 3 a e to the 3t. And then I'm going to go ahead and do a product rule here. The derivative of the... Wait a minute, something happened here. The derivative of the first times the second plus the first, which is at. So there's a t in there. Woo! Right there. Okay, so I'm going to do a product rule again. Hopefully I won't mess this up. The derivative of the first, which is 3a, times the second, plus, this is where I would mess it up, the first, 3a t, times the derivative of the second, which is 3 e to the 3t. Almost coming off the paper there. Okay, there's two of these right there, so let's go ahead and rewrite this as 6a e to the 3t, and then this is going to be plus what we have here. We have 9 a t e to the 3t. Okay, so here we have this one right here, and we have this one right here, and that one right there. We're going to plug that into the differential equation. So let's see what we end up getting here. I think I need another piece of paper. That's what was making me nervous there. Okay, so basically what I have here is, I look at my coefficients here. I have a 1 of these guys, and negative 1 of those guys, and negative 6 of those guys. Okay, I'm going to plug that into the differential equation. So the differential equation looks like this. It's y double prime, so I'm going to write down one of those. So this is 6a e to the 3t plus 9 a t e to the 3t, and then I have minus y prime, which is minus that, so I'm going to get minus a e to the 3t minus 3at e to the 3t. I'm kind of lining up my like terms in the columns. And then I have minus 6y, so minus 6a t e to the 3t. This equals 10 e to the 3t. So look what happens here on this one here. These guys add up to 0. Good thing. 0a t e to the 3t. Those terms that have t e to the 3t that are on the right-hand side of the equation, it looks like there are 0 of them. So that's good that that happened. But meanwhile, the other ones add up to what? This adds up to 5 of these creatures. 5a e to the 3t. And what does that equal? That equals 10 e to the 3t. So 5a equals 10. A equals 2. Okay, so remember that because I'm going to go back to this paper. A equals 2. This guy right here gets a 2. So my final answer then is going to be C1 e to the negative 2t plus C2 e to the 3t. And then this is going to be plus 2, move that out of the way, this is 2t e to the 3t. And I said that's going to be my final answer, but no, not really, because I have to take care of that. So another piece of paper. We are going to take care of that. Now I know you can't see the initial conditions. I could just be a jerk and say, we'll just look at the PDF, but I'll write them up right here. Okay, so the first thing I want to do is perhaps find the derivative of this. So y prime is negative 2 c1 e to the negative 2t plus 3 c2 e to the 3t. And then this one, oh, it's product rule, and I put that there. This is bad planning. The derivative of the first times the second plus the first times the derivative of the second. Ran right into the initial condition, so that hurts when that happens. Okay, so what am I going to do? I'm going to put y of 0 equals 0 in that one, and then y prime of 0 equals 7 in the second one. So the first one's going to give me 0 equals c1 plus c2, and then that's plus 0. And the second one's going to give me 7 equals negative 2c1 plus 3c2, we got to be careful over here, plus 2, because t is 0, and then it zeroes out that one there. So I have c1 plus c2 equals 0, and negative 2c1 plus 3c2 equals 5. I'm going to multiply the first equation by 2. I could be writing augmented matrices. I could just realize that C1 and C2 are opposites, but I'm doing it this way here. I add those equations together and I get 5C2 equals 5, which tells me that C2 equals 1. I know they have to add up to 0, so this tells me that C1 equals negative 1. Whew. So, this was my general solution right here. And so I'm going to put the C1 and C2 into that, and I end up getting y equals C1 is negative, so I have negative e to the negative 2t, and then I have plus C2, so plus 1, so this is plus e to the 3t, plus 2t e to the 3t. And that completes this original problem where I'm trying to solve this non-homogeneous differential equation constant coefficients with annihilators. Now, just so we can see the other method, I'm going to do the same thing, but I'm going to use variation of parameters. And so I'll just write this down. Y double prime minus y prime minus 6y equals 10 e to the 3t. Y of 0 equals 0. Y prime of 0 equals 7. I don't think we'll have to run through that once we get the general solution, but let's just put that down there. And so that's what I'm going to do. And the first thing we want to do is solve the associated homogeneous differential equation, which is y double prime minus y prime minus 6y equals 0. And so this gives me r squared minus r minus 6 equals 0. And this looks familiar, so you know, we are just getting... it's kind of bad that I'm doing it this way. I'm doing it in blue ink because that was... I'm not being consistent with the colors of the ink. Oh well, what are you going to do about that? 3 and negative 2, so the complementary part, which was in black last time, and now it's in blue, and the other part will be in, it will be switched. Oh well, what are you going to do? It is C1e to the negative 2t plus C2e to the 3t. And I kind of wrote it in the same order that we wrote it before, so that's what we want to do when we're doing variation of parameters, is solve the associated homogeneous differential equation. That just means put that thing equal to 0 and see what you get. So the variation of parameters, this is the 9-step program here, where we try to identify certain things. This guy right here, we identify this as f. We see that there's a 1 in front of there. There has to be a 1 in front of there to do this. And we identify some other things. This guy right here, we say, hey, that is y1. And this guy right here is y2. Okay, so we're going to go ahead and compute the Wronskian of y1, y2. So that's of e to the negative 2t, e to the 3t. Take the derivative, so down here we end up getting negative 2e to the negative 2t, and then here is 3e to the 3t. AD minus BC is going to give me 3e to the t plus, okay, because we actually go AD minus BC, but BC is going to be a negative, so we get plus 2e to the t, which is 5e to the t. So there's the Wronskian. Why do we need the Wronskian? Because we are going to figure out, okay, our solution is going to be like this. Our trial solution is going to be C1 U1 plus C2 U2. So our whole variation of parameters is finding out what U1 and U2 are. U1 and U2, we do something called Cramer's rule, and we develop this long process in the notes. And really what we do is we grab onto the formulas here. So U1 prime actually equals negative y2f over Wronskian. So we kind of derive that. And then U2 prime is y1f over Wronskian. And if this were still person-to-person, face-to-face class, this would be something you would have to memorize for the exam. But, oh well, as it goes, let's go ahead and continue this. Negative y2, which there's y2. And then we have f, which is 10e to the 3t. And then this is all over Wronskian, which is 5e to the t. Okay, so that's what we get there. And this looks like it's going to be negative 2e to the 5t. Because we have 6t on the top, and then there's an e to the t on the bottom, so that's e to the 5t on the top. This one right here is going to be y1, which is e to the negative 2t, times f, which is 10e to the 3t. And this is all over Wronskian, 5e to the t. And so what is this giving me? This is actually going to give me, that goes down to the bottom, so that's e to the 2t times e to the t, which is e to the 3t. Those cancel. This just gives me 2. Another piece of paper. Okay. So now I'm going to try to find out what these guys are. U1 is gotten by taking the integral of that. So to do the integral, you can do a U substitution or eyeball it. I'm going to get negative 2/5 e to the 5t. Okay, the c you can take to be 0, just like when you do the method of the integrating factor. And we can take the c to be 0 when we integrate that. I'm going to integrate 2. That's a little easier to do. I don't need a u substitution. This is going to give me 2t. So what I'm trying to do is find the y sub p. So y sub p is c. Gosh. Okay, so that is very embarrassing what I did there. Look at this. This is wrong thing. Should I stop it and edit it out? I don't think so. But it rather is embarrassing. Let's do some touch-up work here. And this is why, like, if you're just watching these for fun and you're not enrolled in my class, what are you doing? I mean, look at the incompetence here. Yp is actually u1 y1 plus u2 y2. Okay, that was silly of me to do. Yeah, that was going to get me in the end if I didn't catch that. I mean, hopefully I would catch that. So Yp is u1 y1. Let me move this down a little so we can see the y1. So u1 y1. y1 is e to the negative 2t. And then we have plus u2 y2. y2 is e to the 3t. So what is this? Y sub p equals negative 2/5 e to the 3t plus 2t e to the 3t. Now, you might be looking at the answer that we got before and getting a little nervous, but I should be the one who's nervous. I'm going to go ahead and put this together with that. So this is c1 e to the negative 2t plus c2 e to the 3t, and then plus the particular solution minus 2/5 e to the 3t plus 2t e to the 3t. Now, before we box our answer and say, oh, that's what it is, notice these guys right here. Those guys, we can factor out an e to the 3t on there, on those ones there, and we end up getting c2 minus 2/5. What is c2 minus 2/5? Well, that's just another constant. You don't see any other c2s out there, so we can write this as c2 e to the 3t plus, and then over here we have c1 e to the negative 2t, and then this is plus 2t e to the 3t. This right here is my general solution. And if we look back on the other problem, I don't know what the other problem is, we ended up getting the same general solution. So it was exactly the same. And I don't want to go through all the pains again to find C1 and C2 given the initial conditions, because it's exactly the same work. So, you know, I'll go dot, dot, dot. In the end, you would end up getting, you know, I'll just write this down again so you could see that you would just do the same thing. And so that's how you do it. Now, so you might be saying, well, why do you use the variation of parameters? The variation of parameters would be good if this said e to the 3t over t, or some driving function that you cannot annihilate using annihilators. So variation of parameters is a very strong method. Annihilators gets things done pretty quickly when you have some common driving functions. Let's see what time it is. It's 30. 34 into that. Let's go ahead and do another problem. So the next problem is this one right here. I'm going to go 10.1a. I have a function f of t, which equals e to the 2t, and then t squared, what do we have? This is if 0 is less than or equal to t is less than 1, and then this one is if t is greater than or equal to 1. And what I'm asking you to find is find the Laplace transform. Oh, another way of saying that is to find L of f. And another way of saying that is to find capital F of s. Okay? And there we have it. So how do I find the Laplace transform? What I have to do first is write down the definition. This goes from 0 to infinity, e to the negative st. This is, this is like if it was a face-to-face class, I'd be like, this is something you should memorize. So we have that right there. There's the Laplace transform. And how are we going to stick this function, this piecewise defined function, into this? It's also piecewise continuous because the discontinuity, I believe, is just a jump discontinuity. So that means we can take the Laplace transform of this. We're going to break up the integral into two parts, from 0 to 1, and then the function that goes there for that part is e to the 2t. And then the next one's going to be from 1 to infinity, e to the negative st. Then we have t squared. And of course, I should be writing my dt's here. So here's the deal. There's actually, this breaks up into two problems. So what I'll do is I'll do each of these problems on a separate piece of paper. And that way we're not overwhelmed. Let's go ahead and do this one first. This one's going to be the simpler one. This is e to the negative st, e to the 2t dt. Okay, we'll come back to that other piece of paper. So how am I going to do this? Well, I'm going to write this as e to the negative st plus 2t dt. This is going to be e. I'm going to factor a t out, and I have negative s plus 2, or I'll write it as 2 minus s dt. Now I'm taking an integral with respect to t. I can do a u substitution, let u equal the whole exponent. I'm just going to eyeball this. I need a 2 minus s, which is a constant right in front of that, so that it can disappear. So out front, I need a 1 over 2 minus s, and then the integral of e to something is e to something. And I'm evaluating from 0 to 1. So I go ahead and put 1 in for t, and I end up getting e to the 2 minus s all over 2 minus s. That's putting 1 in there. Now I'm going to put 0 in for t, and that's going to go e to the 0. So this is going to be minus 1 over 2 minus s. So that gives me the first one. Let's go back over to this piece of paper and write out the answer right below. So the first one here is e to the 2 minus s all over 2 minus s minus 1 over 2 minus s. Okay, so what does this one give? Let's go ahead and do another piece of paper. So this guy right here. So now we're doing this one here, and let me put them up right here. 1 to infinity. I'll rearrange this. This is t squared e to the negative st dt. Now to integrate that with respect to t, I do need integration by parts. I'll put the integration by parts right here. Derivative, integral. I'm going to take the derivative of t squared, which is 2t, and its derivative is 2, and then we have a 0. I'm going to take the integral of e to the negative st. Its integral, this is all with respect to t, is e to the negative st over negative s, e to the negative st over negative s times negative s, which is s squared, and then this is e to the negative st, all over negative s times negative s times negative s, which is negative s cubed. And then this one, who cares? I put my plus, minus, and now I've just computed the integral of that. I'm going to move it over here so I have room, and I'm going to go ahead and say it's this plus that. And if you look at all three of them, they're going to all three be negative. So let's go ahead and write that out. I have. Also, actually, here's a shortcut that we can do. Each of these things, so I'm going to multiply that together and multiply that together and multiply that together and add those three terms. Each of those three terms has what in common? It has this right here. So instead of writing that all those times, I'm just going to factor that out to the front. So this is going to be e to the negative st. And what do we have? We have negative t squared over s. Okay. The next one's going to be minus 2t over s squared from that right there. And then the next one's going to be minus 2 over s cubed. Okay, so we've just taken the integral of this using integration by parts, and we are going to evaluate this from 0 to infinity. Now, when putting infinity in for t, I want that to be 0, and the only way that would happen is if s is positive. If s is positive, this would be like an e to the negative 7t, which would get sucked to the bottom. And you can apply L'Hopital's rule like 2 times here, 1 time there, and you'll find that it all goes to 0. So if s is greater than 0, putting infinity in for t would give you a 0. Okay, minus. Now we're going to put 0 in for t. Okay, so let's just put up those brackets again. We're going to put 0 in for t. This gives me e to the 0 for that one there. And then in here we end up getting putting in, okay, so yeah, that's incompetence. So yeah, don't be telling the president of the college what I just did here, because she'll just fire me, and so will the dean. He'll be like, oh wait, she'll be like that, or the VP. So please keep this to yourself. I forgot to I put a 0 there. Whoops. Good thing I kind of caught it early, because when I put a 1 in for t, I end up getting e to the negative s. So that will change this right here. This is e to the negative s. Okay. And I'm putting 1 in for t. So this is going to be negative 1 over s, and then this is minus 2 over s squared, and then this is going to be minus 2 over s cubed. And of course there's a negative there, and there's 3 negatives there, so when we do this, so this is a negative s, it just doesn't look right. I'm going to go back to this and see if we can write out our answer. Our answer for this part right here is, I'm going to kind of distribute that negative into those negatives, and I'm going to have an e to the negative s. Then I have 1 over s plus 2 over s squared plus 2 over s cubed. That right there is the Laplace transform. We are at the point in this class where you say, I don't know, I don't care about the Laplace transform, and that's all right. But in the next few sections, we're going to see how this Laplace transform solves differential equations that are rather difficult to solve. So that does it for the review. You guys study hard.